So for today, I'm going to be reading through the Meta Chameleon paper, right? So Meta released this new model, Chameleon. They released this paper a little bit back, closer to the release of GPT-4o, and then now they've actually finally released the model. And so I'm just going to be reading through this paper and connecting it to the stuff we've done previously with like tokenization and all that type of stuff. And so we have the paper, we have the draw.io, and let's begin. So, hold on one second. Yeah, cool. Right, so let's begin. So let's start by where we always do. Let's just read the abstract. Let's try to find out what this paper is about. We present Chameleon, a family of early fusion token-based mixed modal models capable of understanding and generating images and text in any arbitrary sequence. Right, so this is in essence an omni model, right? So similar to GPT-4o, except this is an omni model that can just do text and image, right? So yeah, they outline a stable training approach from inception, an alignment recipe, and architectural parameterization tailored for early fusion token-based mixed modal settings. The models are evaluated on a comprehensive range of tasks, including visual question answering, image capturing, text generation, image generation, and long-form mixed modal generation. So they're basically saying they've made a new model and it is natively multimodal. It can do image in, text in, it can do image out, text out. Yeah. And so as they say, Chameleon marks a significant step forward in a unified modeling of full multimodal documents. Cool. Now to actually understand how they did this, let's read the introduction and the other parts of the paper. Recent multimodal foundation models are widely adopted, but still model different modalities separately, often using modality-specific encoders or decoders. Okay, so now let's look at the difference between the previous approach and what this paper is actually saying, right? So, previous approach. I'm going to make the text bigger. Right, so the previous approach. The previous approach was you previously had I should probably... I can use that. Okay, so you previously had the model, and then you had your image input, and then you have your text input, and they were both fed through different parts of the model, right? So in essence, what you'd have is you'd have, say, and then obviously you have your like text out, right? Right, so I should probably extend this over. Right, so you'd obviously have your image embedding, right, and then you'd have your text embedding, right, and here you'd have the core, you'd have like a transformer section, and then you'd have your final output, so your unembedding or your like final head or like whatnot. So I'll just call it unembedding, so it's easy to understand. And so in essence, if you ever had like an image feeding into a model, you had to go through a separate embedding model, right? So what GPT-4 Vision or Gemini, not really, but like GPT-4 Vision did, and other stuff like Lava and whatnot, what they did is they just, whenever they fed stuff to a transformer, they just have like, here's the image that you might get, and here's the text that you are going to get, right? So you give it both pieces of information, and then what you do is you then just do the regular transformer stuff of generating the output. But what this limits you to doing is now your image must be a specific like way to feed it. You can't like intersperse your image within your text and whatnot. And so that's what they're saying the previous method was. Like you have a specific channel for image input, and you have a specific channel for text input, and then you could only do text output. And so in this paper, they present Chameleon, a family of mixed-modal foundation models capable of generating and reasoning with mixed sequences of arbitrarily interleaved textual and image content. Right? So what they're basically saying is, through some method, I'll copy paste this down. I should probably also do something. Like if you had like another image here, red, can put an X to it. I'll just manually put an X to it. right? Like you cannot have just like another image, right? It's illegal. Can't do that, right? And so with Chameleon, which is the new meta model, you can just have another image here, and then I'll just remove the embedding section because we don't know how they've done that yet, and I'll remove the on-embedding section because we don't know how they've done that yet, right? And so yeah, let's just go back to the paper and let's figure out how they've done that. They say this allows for full multimodal document modeling, which is a direct generalization of the standard multimodal tasks. Right? So they're basically just saying, let's just make the most general model, right? That can handle anything. Their unified approach uses fully token-based representations for both image and textual modalities. Right? By quantizing images into discrete tokens analogous to words and text, we can apply the same transformer architecture to sequences of both images and text tokens. And so if we go back to the paper on how an image is worth 32 words, 32 tokens, sorry. They basically just say, hey, look, we can take the image and we discretize it into a one-dimensional representation of the image, right? So they take the image and they say we can have it as a 1D representation, right? And so what Chameleon does, right? And so if we go back to the previous approach, first you obviously had to tokenize it, right? So I want to extend it further, and then I'll talk about the tokenizer, right? So the image and text, they first go through a tokenizer, right? Because this is just kind of necessary. But the image tokenizer, up until recently, would be a 2D set of tokens, right? So you'd effectively have like a 2D set of tokens, and then the transformer would kind of have to handle it, right? So you take it, you have 2D tokens, and the transformer kind of had to handle it, and you couldn't really interweave with text, because then you're interweaving 1D and 2D, and that's actually kind of difficult, right? That's really difficult. Whereas the text would be 1D, right? It's a 1D stream, right? And so then this would go through the embedding and transformer on embedding, and you'd only get text out, right? So I should probably say you get a 1D stream of stuff out. What Chameleon is basically saying is the images, if we have it as discrete tokens, that's also in the 1D format, right? So similar to TyTalk, right, from last stream, they basically take the image and they discretize it and like put it into a one-dimensional stream of tokens, right? So let's build Chameleon up, right? So I should bring the image and text tokenizer in, right? So you'd have the image and text tokenizer. I'm going to draw arrows, right? And then the text tokenizer. And then you just have tokens, right? And so I'm going to use, say, light blue for images and like dark green for text. And so here would be your text tokens, your image tokens. And you can have this be in like any order you want. You can theoretically also have, say, for example, text, image, and like they just have all of them as like a native format altogether, right? So you take everything and you bring it all together. Without the need for separate image text encoders, right? So they're also saying, hey, we only need one encoder. So after it's tokenized, let's just, instead of having separate embeddings, let's just have embedder / encoder, right? So you just, again, what you have now is all of these, I'll put a box on all these. Right, so all of these, you just feed it directly into the embedded encoder, as opposed to here, where it's in two separate streams. You effectively, what you do here is you bring them together into one stream as soon as you can. Right? And then they don't use separate image or text encoders or domain-specific decoders or whatnot. And so they're calling this an early fusion approach. And so if we actually see the diagram differences, with regularly, you'd actually bring these two different modalities in at the transformer layer. What Meta's done here is they've brought the two modalities together in the tokenization layer. Right? So they bring the fusion of the modalities earlier. So they're calling it an early fusion. Right? So you take the multiple modalities, you fuse them together effectively as soon as you can. Right? And so they say this allows for seamless reasoning and generation across modalities. but they're also saying it's a significant technical challenges in terms of optimization, stability, and scaling, right? So they're saying it's really hard to actually scale this up, right? So with regular like vision transformers, we saw this scaled very good, right? The scaling laws were very good for vision transformers, right? With the an image's 32 tokens, we saw scaling laws were very good, right? So these were effectively no-brainers as like state-of-the-arts. With this, they're basically saying, hey, we don't actually know. Well, they're not saying we don't know how to scale. They're saying it's very hard to scale. So there's some issues around scaling there that probably will be fixed as more research happens or whatnot. And as I say, they address these challenges through a combination of architectural innovations and training techniques, right? So in order to scale better, they're just saying, hey, let's use training, let's make the training better, and whatnot. And so they introduce novel modifications to the transform architecture, query key normalization, and revised placement of layer norms. So they're basically saying, we've also modified transformer and stuff, right? So if you look at, say, Vision Transformer, that paper, they were using just base transformer, we're not changing anything. Whereas Meta is like, hey, we're changing some of the transformer stuff to support this mixed modal style. They also show how to adapt the supervised fine-tuning approaches used for text only to mixed modal, right? So now you can align it better. And so using these techniques, they successfully trained Chameleon 34B, which is the biggest model they have, on 5 times the number of tokens as Llama 2, right? So they trained it for 5 times longer. And so they're able to enable mixed modal applications while matching or performing benchmarks. Cool. And so as we can see here, mixed modal output, auto-aggressive LLM, you have your tokenizer, you tokenize the, they didn't have the text tokenizer, but you kind of have the tokenized text, right? And then I should probably have, they have the auto-aggressive LLM, and then they have outputs of tokens. So I should probably bring in the token output, right? So it can clearly do both. So, oh hey, I matched the actual color scheme. Cool. Right. So let's assume it can output both, and then you go through detokenizers, or I call unembedding. Cool. Right. So you have output tokens. I guess output text is, yeah. Right, and then this I said is image. Image, detokenizer. Right, and then you have the text detokenizer. Now, of course, text detokenizers are effectively kind of free because that's just a lookup table. Image detokenizer is a little bit more work, and so as we saw with the an image is 32 tokens paper, this is like an actual machine learning model. It's a vision transformer scale up. It's like a decoder part of an autoencoder, right? And so then, you know, you like feed these images in, you feed the text in, and this is no longer output text because it's output images. This is just output in any modality, right? This is a multimodal native model, right? And so now, effectively, what Meta has done here is, is just they have a natively multimodal model. It can think in like any type of thing. As I say here, you give it the image prompt. You obviously patch it up like a vision transformer. You give it like, what can I bake with this? And it will output a picture of banana bread, and here's a recipe for banana bread. And it will like probably, if it's continued, it'll probably give you the actual recipe for banana bread, right? So, as I say here, Chameleon represents all modalities, images, text, and code. I don't know why they're separating code as a different modality here instead of just text, but there's probably a good reason. We might find it out later in the paper. As discrete tokens and uses a uniform transform-based architecture that is trained from scratch in an end-to-end fashion on 10 trillion tokens, right? So remember, Llama 3 was trained on 15 trillion tokens, and that is quite famously probably the largest number of tokens a model has been trained on, right? So Llama 3, largest number of tokens a model has been trained on. Here they've trained for 2/3 of that, right? Like it's a very large training run. And so as a result, Chameleon can both reason over and as well as generate arbitrary mixed modal documents and whatnot, right? And so text is in green, images in blue, and so as you can see, here you go. What we can also see here is that they have start image and end image tokens, right? So they're probably doing something fancy here where, yeah, and so then you can like say start image, and it will output. And so in some, and they're basically saying static benchmarks is not good enough, right? So because this thing can do all the modalities, right? So you need some more benchmarks to be able to do stuff. And so they carefully designed human evaluation experiment. So they basically made a new benchmark, right? That's basically like, hey, who is, like which is a better model? And surprise, surprise, their model is the best model out there, right? Okay, cool. You made a new benchmark, your model's the best. There's some red flags about that, but after trying this model, I can kind of say, yeah, makes sense, right? It's natively multimodal. In a similar way to how GPT-4o is if OpenAI actually allowed the native multimodal stuff. So they made Chameleon, they have some new architectural innovations, they have state-of-the-art performance across a bunch of benchmarks, and it's competitive on text-only tasks, and they can also do image generation in the same model, and they have the large-scale human evaluation. Cool. Oh, they have an example here. So the prompt, I'm bored, could you show me some cool, quick-looking birds and tell me about them in 2 to 3 sentences? And the model, quite amazingly, will go and just start talking about the stuff, and it will have like generate an image, right? This is not a real picture of a Kiel build token, right? This is a picture that was generated by the model in these image tags. It'll talk about puffins and yeah. And so the samples are interleaved image and text generation, right? No, they did actually let the image generation part of this loose because safety reasons, right? So now, yeah. So pre-training. Now I'm talking about the pre-training step, right? And so they use the scaling properties of transformers, right? Because transformers scale very well. So they present any ordering of images and text during training, ranging from text only to single image text pairs to full interleaved text image documents, right? So they can just feed it in straight up like PDFs or whatever. And so the PDFs can have like graphs or whatnot. So the prompt, they give you a picture of a stop sign, analyze it, and then just talk about it. And so this is just another thing of how it works. And so we'll like talk about like challenging spots for Chameleon and like the optimal patterns and whatnot. Image tokenization. They train a new image tokenizer based on Gaffney et al., which I believe that's the VQ-GAN. That's the, I believe that, is that VQ? I should probably double check that. Let's actually go one step deeper. Let's actually look at this Oxford link, right? Right. Abstract. Yeah, it's based on vector quantized various like VAs. So, is this VQ GAN? Okay, it's based on VAs. This is the older method that the image-associated tokens or TyTalk is trying to replace, right? So, in essence, this is just, this is the older method, but you could just substitute that in there. And so, they trained a brand new tokenizer over a subset of the training data outlined below. The vocab size is 65,000, which is is that 2 to 16? I think that's 2 to 16, right? It's 2 to 16, which includes 8192 image tokens, right? So 8,000 of those are image tokens, and the remaining like 58-ish thousand is text tokens. And so they use a sentence piece library. And so then there's another example of what it does. What can I bake with this? Yeah. They're clearly very proud of the model. They're showing it off. And it's a very good model, right? So we talk about the pre-training data, right? So it's 2 stages. The first stage is 80% of training, while the second is 20%. And so the text-image pairs, they rotate so that 50% of the time the image comes before the text, right? So basically whenever they have, like, say, an image and like a caption, sometimes they have the text before the image, so the model will actually generate the image. Or the other times they'd have the image before the text, so it's like caption, right? And so the first stage is they have a data mixture, right? So they have some text-only data sets, which includes a combination used to train Llama 2 and Code Llama for nearly 3 trillion text-only tokens, right? Stage 1, they train 3 trillion text-only tokens. And so, they have their training curves. They have some text-image stuff, and so it's a publicly available data sources and licensed data. And so the images are resized and cropped to 512 by 512. And so in total, 1.4 billion text-image pairs, which is 1.5 trillion text-image tokens. So you already have 4.5 trillion tokens here, right? And then They procure data from publicly available web sources, not including from Meta's products or services, right? So they're basically saying, hey, we don't have to train on Facebook or Instagram data. This is all public data. None of this is metadata. For a total of 400 billion tokens of interleaved text and image data, similar to, right? And so they do the same filtering for images that was applied to text to image, right? So they sometimes swap the orders or whatnot. And so this is, in essence, 5 trillion tokens. And this is 80% of the training time, right? And so they just train on like basically everything, right? They're training on everything 80% of the time they've learned, right? It's a model, it can learn pretty good. In the second stage, they lower the weight of the first stage data by 50%. So only half is this lower quality data. And they mix in the higher quality data sets while maintaining a similar proportion of image text tokens, right? So they keep the ratio of images to text the same, but then they've introduced higher quality data sets, right? And so they include a filtered subset of the trained sets from a large collection of instruction tuning sets. So this is the second stage is also your like instruction tuning stage, right? Where you give it the instruction format and stuff like that. And so they basically say it was challenging to maintain stable training when scaling Chameleon models above 8B parameters and 1 trillion tokens, with instabilities often arising very late in training. So they adopted the following techniques so that it's not unstable. And so, as we can see in the stuff here, uncontrolled growth of output norms is a strong indicator of future training diversions, right? And so, their output norms are just going up like crazy, right? And so, output norm is kind of a step of like how good the model is, but if it's going up like crazy, that something is going on there, right? Like you don't know what's going on. So the architecture, right? So it's Llama 2. They use OMS norm. They use Swigglue. They use Rope, right? So they also recently released a paper on COPE, so contextual positioning encodings, and so that's probably the paper I'm going to do next, which is a new way to do positional encodings for models, but that's later. And so they found that the standard Llama architecture so divergences, as they said before. And so, because you're training with multiple modalities of significant entropy due to right? They're basically just saying multiple modalities kind of screws up the stuff, right? And that makes sense, right? So all of their previous models, they've been text only. They're kind of doing stuff on entirely text models. And so they've kind of optimized their learnings and processes for like text only models, right? Like Llama 2, Llama 3, they're all text only models, right? And so now here they have to like change it. So now now they're like architectures work better for images, right? And so the Vision Transformer, they have one, like people and whatnot, they have the stuff for images, but it's not optimized for text. So the meta people here have to find a fine balance between the two for all this stuff, right? So basically you have entropy due to softmax, you share all the weights of the model across all modalities, so each modality tries to compete by increasing its norm slightly, right? So in essence what you have here is you only have so many parameters, right? You only have so much. And so now when you're training the model, let's assume, just so happens that, let's assume you have the 34B model, and let's assume 17 trillion parameters are text and 17 billion parameters are images, right? Now, that's not probably how it works. It's probably a little bit more interleaved and whatnot, but yeah. So now what they're saying here is the text generation parameters, like if they had, say, too much text in the data set, they'd overpower the image generation ones, right? And so the text generation would effectively take over, and it'd be terrible at images. But if they had too many images, the image generation part of it would take over, and then it'd be terrible at text, right? So they had to find a fine balance there. And so in Figure 6b, that's later, they basically say if you disable image generation, there's no instability issues, right? Sometimes it's generating too many images. And then, yeah, so each modality is competing. It's not programmatic to start, but it diverges once you go outside of BF16. And so in a unimodal setting, the problem has also been maybe a large drift problem. In 5a, they plot norms, right? So we've talked about that before. Then they say softmax occurs in two places. So another big issue is with softmax, right? So softmax, as they say, softmax of z is equal to softmax of z plus c, because, they can't differentiate between the two. And so it's softmax is in the attention and the softmax over the largest. So the softmax over the largest is at the end. I don't know if that's too useful for finding loss, but core attention, the softmax there, that's causing issues here, right? So first they deviate from Llama by using query key normalization, QK norm. And so QK norm directly controls the norm growth of input, right? So basically saying you have a new method of applying layer normalization to the query and key vectors within the attention, right? And this way it doesn't do some funky stuff. And so as you see, the training curves for 600,000 steps for Chameleon 7 and 34B over Mixed-Modal data, and you can see this is training very nicely, right? The training curves are exquisite, I would say, right? And then the loss curve with image generation disabled is like, hey, you don't have instability at all. And 34B using dropout does not fix divergences, and so as you can see, wow, you have some crazy spikes, right? Without norm reordering. But with norm reordering, which they talk about later, you don't get those crazy spikes, right? So it's more stable. It's more of a stable training curve. And so to stabilize 7B by Chameleon, they have to introduce the dropout after the attention and feed forward layers. And so it's not enough to stabilize 34B. So 7B, you're able to get away with a small amount of stuff because it's a smaller model. But with 34B, you kind of need to put in more effort to stabilize it. So they use the strategy normalization performed by somebody else within the transformer block. So they tried it, and as we can see, it's norm reordering, and it does better. So we can actually see the hidden vector after attention, right? So let's look at llama 2, which is what it was previously. So the hidden is the like input to the attention block plus attention of the attention normalization, and the output is this one plus the feed forward and feed forward norm. What Chameleon is doing is they're doing the normalization after they feed it through attention, right? So because now you've normalized it at the end of the layer, you still technically have a fully normalized input to the attention layer. But now because you're normalizing it after, you don't actually get a lot of the instability issues, right? So now, yeah, you just don't get the instability issues. So optimization, these are the exact settings. They use AtomW with beta 1 2.9, beta 2.95, epsilon of 10 to the minus 5. They use exponential decay learning schedule. So the GPT series, the cosine decay, this is exponential decay. I don't think it particularly matters, but yeah. So they warm up over 4,000 steps and the exponential decay to the learning rate to 0. And so they apply a weight decay of 0.1 and global gradient clipping at 1. And they just have specific settings, right? Specific settings for training the model so that it's a lot, nicer to work with and whatnot. So for Chameleon 7B, it was important to use both dropout and Z-loss to reduce stability, while Chameleon 34B required only Z-loss, right? They didn't have to do dropout normalization and whatnot. And so Chameleon 7B was trained on 8 million tokens batch size, and 34 was 12 million token batch size. And they do 2 epochs of the entire training set, right? Over 9.2 trillion tokens doing training. And so they show the first 600k tokens. What? Oh, they show the curves. That was the curves. And so here's the core architectures and optimizations in Chameleon compared to Llama 1 and 2. They didn't actually include Llama 3 here because Llama 3 was basically just released when this paper came out. So, yeah. So, context length of Chameleon is 4k tokens for both. GQA, they only have it in 34B. Tokens learning rate, this is just more specifics of how much they've learned and whatnot. The pre-training hardware, it was on Meta's research supercluster, and alignment was done on other internet research clusters. They use A100s on both environments. So Meta's been buying a lot of H100s. They clearly didn't use those for this training project, but they probably will in the future. And so the research supercluster employs some technology. And here's the GPU usage. So Chameleon ran on 1,024 GPUs for a net total of 856,481 GPU hours. If I plug that into a calculator, so if I do 856,481 divided by 1024, they trained us for 836 hours. So if you divide that by 24 hours, it was training for effectively a full month solid, right, on both of these, right? So 34B is 3,072 concurrent GPUs, and it was like, this is a lot of training they were doing, right? Like most of us will never get access to this kind of training compute. And so it's good that Meta is actually opening these models, so now we can effectively leverage their stuff and then fine tune and do that type of stuff. And so then inference. They're talking about how to actually inference these models, right? So they're basically saying there's performance issues with inference time, right? So data dependencies per step, and so the decoding information changes whether the model is generating images or text at a particular step. Right, and so if we go back up to the actual model page, based on that reading, we can know that these tokens here are actually the same. like tokens as the text tokens. The only reason they're labeled as images is because you have the start image and end image tokens, right? If those tokens weren't there, those would be labeled as text, right? So the model got really good at seeing the start image, and the stuff it was outputting was image only. Now, further research from this point is, what if those were just different tokens, right? So you have like just like set of tokens above the like match. So if you had like 50,000 tokens and 10,000 image tokens, instead of those occupying the same numbers, the 10,000 image tokens will occupy, say, other numbers, right? So that's future research that people can do, right? And so if we go back down to the infinite step, and so the tokens must be inspected at each step, and so copy from the GPU to CPU. So then you have some like slowdowns because it takes time to move data from the GPU to the CPU. You masking for modality constraint generation. So if you're only doing image only generation, tokens that don't fall in a particular modality must be masked and ignored when detokenizing. So if you like type in like an image generation prompt and it outputs some text as well as the image, you have to like mask the text, and it's a whole problem. And fixed size text units. So unlike text only generation, which is variable length, token based image generation has fixed blocks, right? So it's the fixed size. And so that causes some issues on inference time. And so they built a standalone inference pipeline on PyTorch with GPU kernels from Xformis, right? So they're using the tech and they solve the problems, but it's hard, right? It supports streaming for both text and images, and so they've solved the problems, but it was hard to say, right? And so they're fine-tuning data set, right? So this is their like inference and stuff like safety and whatnot, like making sure the model's not like racist or whatnot. You have pure text and code, and so you only have 1 million tokens of code, but 940 million tokens of text. Visual chat, so like chat, like talking with the model, but then sometimes there's images and whatnot. It's 20 million tokens there with 17,000 images. Image generation is 70 million tokens and 65,000 images. And so based from this entirely, we can see that, an image is roughly 1,000 tokens, right? So the TyTalk people, an image is 32 tokens. Here an image is 1,000 tokens, right? So it's a lot less efficient, but if they implemented that, you could theoretically have a way more efficient model, right? Interleave generation, and they just have more stuff. They have safety, so image safety and whatnot. And so they separate their fine-tuning data set into the following categories, and they have it in there. And so they inherit the text data set from Llama 2. So it was trained, the fine-tuned the same way as Llama 2. Now, of course, Llama 2's instruct fine-tune wasn't actually very good, right? Llama 3's was much better, but this isn't the point of the paper. The point of the paper is not to make Llama 3, which is just improvement on Llama 2. The point of the paper is to show a mixed modality setup, right? And so there you go. And so for the image generation one, they curated highly aesthetic images by applying and filtering image in the licensed data set. So they got a bunch of data, and then they like filtered it down to a bunch of good images, right? Top 64K images. And so then, safety data, they had a collection of prompts that could potentially provoke the model and provide unsafe content. So they basically just have a bunch of stuff like, if the user asks to make images of violence, like, hey, just say you can't help with that. If they ask to talk about sexual content, just say, nope, can't do that, right? So it says, I can't help with that. They have synthetic stuff generated with rainbow teaming, and a bunch of stuff to basically just make the model safe, right? So they can actually release it. So for fine-tuning, they have a bunch of stuff, and so here's some examples. Can you make a poem? Here's a poem. Give it an integers, here's some code. Renaissance Square, make an image, right? Image generation, visual chat, this is what visual chat is. You give it a picture and a prompt. So this is what previous mixed modal models would do, right? So you give it the image and the prompt. It's in like two separate things. Like as you can see, it's not interspersed, and then it gives you a response. Here's what we can do now with Chameleon. You have interleaved text and image generation, right? So it generates text, then it gives an image, then it generates text and then another image, right? So you can interleave it, and it's nice to work with. And so then they have some more stuff of like task categories and examples of prompts, and you can ask it, hey, show me a Middle Eastern alternative to some dishes, and it will give you those stuff. Write me an introduction to a story. What's the difference between these two creatures and whatnot, right? You can ask it stuff. It's just like an LLM, but now you can output text as well as images, right? They can do both. They have some human evaluations, task fulfillment rate. So if you look at how often the model fulfills tasks, as you can see, it fully fulfills more than the other top models. It fulfills less, like it doesn't partially fulfill as much, and it doesn't fulfill a small percentage of them. right? And so Chameleon versus the baseline, Chameleon wins most of the time against Gemini. It wins more often than basically every other model for mixed modal tests, right? Like human stuff. And we can probably skip some of the evaluation stuff, right? But this is just, yeah. It's like, hey, look, they beat the other models, right? They do some safety testing, and they're basically saying this is the best, right? And so here's the benchmarks, right? This is some stuff people actually care about, right? So Chameleon, Llama 2, Mistral, Gemini Pro, GP4. So on HelloSwag, 76%, 35 is 85%. So this is a pretty good model. It's not a GPT-4 level text-based model, but that's not the point of this, right? The point of this is it's images and text together, right? MMLU. They also do stuff on image captioning, and they compare it to other image captioning stuff. So they compare it against the old Flamingo. There's a new Flamingo. There's Flamingo 2, which is a lot smaller and a lot better, right? But they're comparing it here. As you can see, Chameleon is just the best, right? Now, of course, the new stuff's out. Of course, Gemini Pro is, Gemini Pro is still a pretty good model, right? But then they talk about related work, right? And then they have the conclusion, right? And so, if we go back to the draw.io, in essence, the core improvement that Chameleon does, I should probably move all of this stuff down. Basically, the core improvement of Chameleon is that you effectively bring these together earlier, right? So I should probably put a box where the tokens get brought together. Right. So previously, the tokens would get brought together in this step. But now, what you've done is you've pulled it earlier, right? So you've pulled it basically immediately after the tokenizer. You pull it like effectively like a full step behind. And so now the model, the embedders are able to logic over these images and text pieces. And so, yeah, so now they've brought that in, and then they've actually released the model. You can actually just go to Meta Affairs like website and like ask for access to the model, and then they'd like give you access. It's a research license, so you can't use it to make money or anything, but you can use it to test the model. Note, they've also disabled image outputs, right? So all the fancy multimodal stuff, not there yet. It's going to be released soon. It's just it's not released yet because safety, and they don't want people making like illegal content with this or whatever. So, in essence, you can actually try out the text model. You can try out image inputs to this model. You can basically try out the model and everything except image generation, which is probably one of the coolest parts of this model, but we don't have that yet. It's also the new part of this model, so we don't have that yet. Wait a little bit, the model will probably come out, and yeah, that's the paper, that's the new model. Next time, I could go over, I'll pick some model, I could go over attention is all you need, I could do a stream just trying out Claude 3 Sonnet or whatnot, and yeah. So, that's basically it. And I will see you guys all in the next stream.